we are talking about neighborhood operators. So this is the outline. We'll have a first introduction, and we will, in the second part, we will introduce symbolic neighborhood operators. And in the third part, we will introduce in-stream-related neighborhood operators. Finally, in the fourth part, we will introduce linear shift invariant neighborhood operators. So let's begin our introduction. The so-called neighborhood operators is mainly used for low-level vision. The low-level vision is some features like grouping, color, spatial frequencies, and low motion. And for mid-level, we will have like textures, surfaces, global motion, depths, etc. For high level, we are like given you a boundary and given you boundary or the contour, and you want to extract the feature. So the high level vision is like objects, characters, actions, and intentions. So the definition of an neighborhood operators is a function that takes input of the position xy and the pixel of the image at xy, and also the pixel value of the neighborhood positions, and also and take these into as inputs and generate the new output image at xy, and sometimes the new the the newly generated output will be served as one of the inputs of the neighborhood operator. So neighborhood operator can be classified uh, according to three aspects. The first is the domain. The second is the neighbor. The type of the first is the type of domain. The second is the type of neighborhood. The third is the type of recursiveness. First, we will discuss what is a type of domain. There are two types of domain. The first one is numeric. So if a neighborhood operator that have a numeric domain are usually defined in terms of arithmetic uh, operations such as addition, subtraction, and calculating minimum and maximum, etc. And a neighborhood operator that is symbolic are defined in terms of the Boolean operations like and, or, not, or a table lookup operation. This is the first classification in terms of the type of domain. The second the second aspect is neighborhood. Uh, in this chapter, we will only consider two types of neighborhood. The first type is a 4-connected neighborhood, and the second one is 8-connected neighborhood. So a 4-connected pixel are neighbors to every pixel that touches one of their edges. So this one touches one of the XY edge at left, touches this one touches the edges at the bottom. This one touches the edges at the right. This one touches the edge at the top. For 8 connected neighborhood, and 8 connected pixels are neighbors to every pixel that touches one of their edges or corners. Okay, so in addition to the 4 touches the edges, will have additional 4 touches the corner here. The corner is the intersection of 2 edges. Okay, here and here. So this is a 8 neighborhood. So neighborhood might be small, like this one, and asymmetric. This is not symmetric, right? So that it only contains only one nearest neighbor. Okay, this is possible, and it can also be large, that it contains m times n neighborhood centered around the given position. But these 2 cases will be out of our concern in this chapter. The third perspective of classifying a neighborhood operator is the recursiveness. Basically, recursiveness is defined based on whether the generated output depends on the previously generated output. So for non-recursive neighborhood, the output is only a function of an input image neighborhood related to the output pixel position. So for our recursive neighborhood operators, the output will depend in part on previously generated output values. So this is a difference. So in terms of memory, you can think a recursive operator is sequential, and a non-recursive neighborhood operator is parallel.